I am Dr. PSV Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the optical fibers construction, working and some other principles too. At the end of this lecture, the student will able to understand the construction of an optical fiber and you can derive the acceptance angle, numerical aperture expressions also. So coming to the construction of an optical fiber, same, every optical fiber essentially contains three major parts. First one is core, cladding and the sheath or buffer. These are the three major parts of every optical fiber contains these three parts. These are three coaxial cylinders. The inner cylinder is called core and the outer one is called cladding. This is the cladding material and the outer jacket or say that sheath that provides only mechanical strength to the cable. The most important the materials or the regions are core and cladding. Actually, core and cladding are made up of the same kind of material, maybe glass or plastic. Of course, here there is one condition, the core is doped with impurities to get the fractional index difference. Means here the refract index of the core N1, the refract index of the cladding it is N2. Our condition or the essential condition N1 must be greater than N2. Of course, because of the fractional index difference, this N1 say suppose it may be 1.5, this N2 may be 1.499, something like that approximately. So like that actually core and cladding are made up of same kind of materials. Because of some impurities, addition or doping, the slightly change in the index, that is N1 is greater than N2. Once again, every optical fiber essentially contains three major parts: core, cladding, sheath or buffer. That sheath or buffer provides only mechanical strength to the cable, whereas core and cladding are made up of either glass or plastic. Here, the inner cylinder, it is called core. The next, it is surrounded by another coaxial cylinder called cladding. This is the cladding material. And the remaining part gives only the mechanical strength to the cable. The major principle of the propagation of signal is the total internal reflection, TIR. After all, core and cladding are made up of either glass or plastic. When the light enters this cable, there is a chance of escaping from the cable. That's why there is one important principle, that is total internal reflection, TIR. That's why to maintain that one, core is having the refract index N1, cladding is having the refract index N2, and here the condition is N1 is greater than N2. Coming to the total internal reflection, just observe, whenever say this is the denser medium of refract index mu2 and this is the rarer medium of refract index mu1, say. When the light is traveling from denser to rarer, of course it bends away from the normal. Say the incident angle is I, angle of refraction R. As we are increasing the incident angle, angle of refraction increases. At a particular incident angle, say that is denoted by theta c, then the light travels along the boundary of separation. Without suffering refraction or reflection, at a particular incident angle theta c, light travels along the same region. Means along the boundary of separating these two media. That angle is called critical angle. Suppose if the incident angle I is greater than theta c, what happens? Again, the light ray will be reflected back into the same medium itself. Means the angle of refraction increases, that will be refracted back into the same medium itself. That means total internal reflection means two conditions we should satisfy. One is the light ray should travel from denser to rarer medium. Second condition, incident angle must be greater than the critical angle. Then what happens? Light will be reflected back into the same medium itself. That phenomenon is called total internal reflection. You observe the core refract index N1, cladding refract index it is given by N2, and N1 is greater than N2 means core is denser medium, cladding is the rarer medium. So the light is traveling from denser to rarer, it will satisfy the total internal reflection so that it undergoes the total internal reflection within the core itself. What should be the incident angle so that the light undergoes the total internal reflection? What must be the maximum angle? the maximum limit of the angle is denoted by theta m, and here we are taking alpha m say. This is called the maximum limit of the angle. It is called acceptance angle. So within that one, if the light ray is incident, that undergoes total internal reflection. If the light ray makes the angle more than that one, it escapes from the cable. So we have to determine the expression for the acceptance angle. Every optical fiber that accepts up to a certain limit of the incident angle, beyond that one it doesn't accept it. Anyhow, we are going to derive the expression for this alpha m, acceptance angle. Okay, coming to the diagram figure in this one. Here, this is the inner cylinder is denoted by core, and the outer one, it is taken as cladding. Sheath or buffer, it is not at all required here. It is providing only the mechanical strength to the cable. Now you just observe, wherever there is a reflection and refraction, we can apply the Snell's law. So coming to the Snell's law, suppose here our assumption, the core refractive index is N1, cladding refractive index, it is denoted by N2, core refractive index is N1. Okay, and the incident angle, it is denoted by alpha I, angle of refraction alpha R. So let us take like that one, apply the Snell's law at this core and cladding interface. So applying the Snell's law, what we get? Observe, N0 sin alpha I is equal to N1 sin alpha R. Alpha I is the incident angle, alpha R is the angle of refraction, and N0, N1, N0 is say this N0 is the refractive index of the air medium or any other medium. Suppose the cable is immersed in the water, say, then N0 is taken as 1.33 something like that. It is immersed, it is kept in the air medium, N0 is equal to 1. Anyhow, the light ray is initially traveling in the medium whose refractive index is N0, and the core refractive index is N1, cladding refractive index is N2. First you observe at the point A, there is a refraction of the incident beam. That's why we can apply the Snell's law. Observe that one, N0 sin theta is equal to N1, alpha is equal to N1 sin alpha R. Alpha R is given by 90 minus theta. Actually, you observe at the core and cladding interface, the angle is taken as theta here, theta. So what is the total angle here? Suppose you observe 90 degrees. This is given by alpha R, the above also alpha R will be there. Total in this one, in a triangle, the total angle is 180 degrees. That's why the above at the point C, the angle is given by theta, and angle of say the refraction, it is given by theta, or the angle here it is 90 degrees. Therefore, what will be this theta R will be 90 minus theta, or alpha R will be 90 minus theta. So from that you substitute, what is sin 90 minus theta? Sin 90 minus theta, you will get cos theta. Therefore, what is the equation now we have? N0 sin alpha is equal to N1 cos theta. So this is some important equation now. Later on we discuss again this one. Now keep it aside. Let us take, I want to introduce one new angle, alpha m or some alpha m at this one, in such a way that if alpha is equal to alpha m, then the angle of refraction in such a way that again theta, this theta is making the critical angle theta c say. You observe the first one, if theta is less than the critical angle theta c, the light ray will be lost by refraction. When theta is equal to theta c, alpha is equal to alpha m, it is the maximum value. Actually, there are three cases possible at any light ray incidence. That means either the light ray may escape from the cable, the light ray may travel along the boundary of separation, the light ray is reflected back into the same medium. Three chances are there. In the first case, that is refraction, nothing but the light will be lost. The second case, the light ray is incident at the critical angle, without suffering any deviation, it travels along the boundary of separation. If the incident angle theta I is greater than theta c, what happens? It undergoes total internal reflection. Three cases are possible. Now I just analyze this case. That means the critical angle theta is equal to theta c, it is incident at core and cladding interface. For that one, what should be the incident angle? Alpha m. I am taking this condition, that means at theta is equal to theta c, alpha is equal to alpha m, it is the maximum value. I am just introducing like that. It is the acceptance angle. If alpha is more than alpha m, what happens? Then theta will be less than theta c, that escapes from the cable. Understood? So anyhow, suppose substitute the same thing in the above equation here. What we get? N0 sin alpha I. Alpha I is nothing but alpha m. It is equal to N1 cos theta, nothing but theta c. I am taking this equation. Therefore, sin alpha m is equal to what we get? N1 by N0 cos phi c we get, or theta c. Here, so what is this theta c? Again, you apply the Snell's law at the point C. If theta is equal to theta c, apply the Snell's law. What do you get? N1 sin theta c is equal to N2 sin theta, theta means 90 degrees. So, apply, then theta c is equal to sin inverse of N2 by N1 we get. This is theta c or sin theta c. Then from that, what is cos theta c? Under root of 1 minus sin square theta c, or it is under root of N2 square by N1 square we get. That is cos theta c. Substitute the same thing in this equation. Suppose you take it as equation number 1. So, from equation 1, what we get? N0 sin alpha m is equal to N1 root over N1 cos, that is theta c, mean nothing but root over 1 minus N2 square by N1 square. From this one, you simplify, you will get sin alpha m is equal to root over N1 square minus N2 square by, actually we get this as N0. In case of air medium, N0 is equal to 1 you can take. In any other medium, you have to take N0 value. So, this is the expression for the acceptance angle alpha, or alpha m is equal to sin inverse of under root N1 square minus N2 square by N0 is equal to 1 we get. This is the expression for acceptance angle of an optical fiber. Once again, simply what we have to understand here is, the light ray is traveling from the air medium or any medium, making the incident angle alpha I. Here, the refract index of the air medium or anything, it is N0, core refract index is N1, cladding refract index is N2, and this light ray, again it is reflected into the same medium at the point C, undergoing TIR, total internal reflection. Simply we have to apply the Snell's law at two places. One place air core boundary, second one core cladding boundary. Apply the Snell's law at two cases, air and core boundary, core and cladding boundary at the point A, at the point C. Two times we are applying the Snell's law, and finally we are getting sin alpha m is equal to root over N1 square minus N2 square, where N0 is equal to 1 for air medium we are taking. This is the expression for the acceptance angle alpha m. It is the maximum limit of the angle within that one light ray should incident. So, anyhow, next there is another point, numerical aperture. Actually, theta m is the acceptance angle. What is sin alpha m? That is the numerical value. So, the numerical aperture, it is called the numerical aperture. Alpha m is the angle, sin alpha m is the numerical value, it is called numerical aperture. It is given by root over N1 square minus N2 square. So, this is the expression for the numerical aperture. There is another one more important point, delta. Delta is called fractional index difference. Delta is equal to N1 minus N2 by N1. N1 minus N2 difference of the refract indices divided by N1. That means it is a fractional index difference. So, what is this N1 minus N2? N1 minus N2 is equal to, we get N1 into delta. Actually, here what we are writing, root over N1 square minus N2 square means N1 plus N2 into N1 minus N2, or that N1 minus N2 is written as N1 into delta, and N1 plus N2 can be taken as 2N1. Why? Because the difference between N1 and N2 is very, very small. N1 is 1.5 say example, N2 1.499 something like that, very, very small difference. During the difference, you cannot take it as 0. During the addition, you can take approximately equal. That's why why n1 plus n2 is taken as 2n1, n1 minus n2 is taken as n1 into delta. Therefore, what is the numerical aperture now? Na is equal to n1 into root over 2 delta, where delta is the fractional index difference. There is another formula for this Na. Initial formula, Na is equal to root over n1 square minus n2 square, and another formula in terms of delta, Na is equal to n1 into root over 2 delta. So, this is the another formula for the numerical aperture. So, actually in this topic, what we have discussed is what is the construction of an optical fiber, what are the major parts of an optical fiber, core, cladding, outer sheet, buffer, etc. What is the condition for the propagation of light? So, that is total internal reflection, and afterwards what should be the maximum angle for the propagation of light, that is the acceptance angle. Later on we have discussed the numerical aperture in terms of the fractional index difference also. Okay, thank you.